Officer. I'm joined today by my two Deputy Press Officers. Inga Heyer in the back will be monitoring the webcast and relaying questions from off-site journalists. And Larry Marshall will be manning our roving microphone during the Q&A. Please silence your cell phones, pagers, beepers, etc. And in the next couple of minutes, 3 press releases from Sloan Digital Sky Survey will be winging their way to your inbox if you're on our press list. So the way these briefings work is I will introduce all the speakers, then I'll turn it over to the first one. They'll make their presentations in order, and then we'll have questions and answers at the end. First, I want to make a couple of real quick announcements. Today was the NASA Town Hall during lunchtime, and the 2 principals who spoke there, the Associate Administrator for the Science Mission Directorate, Thomas Zurbuchen, and Paul Hertz, the Director of NASA's Astrophysics Division, will be available to the media in Pecos 2 on the hotel side of the bridge, Paul at 3 o'clock, Thomas at 5 o'clock. So if you're interested in that, please head over to Pecos 2. If you haven't signed up for the press dinner yet and you want to come, please sign up in the press office. And there's another sign-up sheet there now, looks like this. If you're interested in interviewing our 10 and 13-year-old presenters, Cannon and Carson Huey, their mom and their teachers would like to limit the number of people who descend on them at once, and so we've created a little sign-up sheet to avoid having them get real nervous. All right. So this press conference features results from the Energizer Bunny of sky surveys, the Sloan Digital Sky Survey. If you've been coming to these meetings regularly, you've had the pleasure of attending quite a few press conferences based on the Sloan Digital Sky Survey because it's been going and going. This time we're going to hear not just about some of the science, but also some other innovative programming that is helping to point the way for the astronomical community. We're going to hear first from the scientific spokesperson, Karen Masters of the University of Portsmouth in the UK. She's going to talk about one of the Sloan Survey's projects, the Apache Point Observatory Galactic Evolution Experiment, or APOGEE, and she's going to specifically talk about how it's going south in the best possible way. Then we have a tag team from New Mexico State University, Sten Hasselquist, that is not Stan, it is Sten, and John Holtzman. They'll be talking about elements of life in the Milky Way from the APOGEE survey. Then Johanna Teske from the Carnegie Institution for Science is going to ask, can Garnet planets be habitable? Garnet planets, of course, being between a rock and a hard place. And then finally, Kelly Holley-Bockelmann, who's on the AAS Council and who is at Vanderbilt University, is going to talk about Sloan's efforts to foster inclusivity in astronomy. And if you attended the town hall yesterday afternoon, you know that the community is definitely very interested in that question. So I will now turn it over to Karen Masters. And we should be good to go. Yep, we're good to go.
Thank you, Rick. As Rick mentioned, I'm Karen Masters. I'm a reader in astronomy and astrophysics at the University of Portsmouth in the UK, and I'm the spokesperson for the Digital Sky Survey, the Sloan Digital Sky Survey. Again, Rick introduced this very nicely. We are the Energizer Bunny of sky surveys. We've been going for 17 years now with approximately annual data releases. We have a data release planned for 6 months from now, so you'll be hearing about that in about 6 months. We're probably most famous for the imaging at some level. The images from the Sloan Digital Sky Survey cover 35% of the sky. And we've used those images to target more than 4 million astronomical objects and take their spectra. These data, because they're made public, have resulted in a huge contribution or a huge amount of papers in the scientific field. Over 5,000 papers cited collectively more than 200,000 times. We're still taking data. We're currently in the 4th phase of the Sloan Digital Sky Survey, which is planned between 2014 and 2020, so we're just about 2 years in. We are still welcoming institutions to join our collaboration. We wanted to share that. And these are the surveys that we're currently taking data for. We are exclusively now a spectroscopic survey. We are no longer taking images. We are taking spectra of stars in the Milky Way galaxy in the Apache Point Observatory Galactic Evolution Explorer, or APOGEE experiment. The EBOS experiment is the extension of our Mapping the Universe program. We're taking a spectra of distant galaxies to measure their distances, map the large-scale structure to larger distances than we've done before. And the MANGA survey is our new galaxy survey, where we're taking multiple spectra across the face of galaxies in order to map their internal structures. Okay, so we make this data publicly available, so why would an institution want to pay to join the Sloan Digital Sky Survey? And because we have a press item on our efforts for inclusion and talking about our collaboration, I just wanted to highlight that we are a big collaboration. We have more than 500 scientists in institutions all over the world. More than half of our scientists are now not in the United States. We have members in Europe, Asia, all over the world. And this is just a wonderful group of people to work with and do science with. We get a lot done. And you get access to the data earlier than we make it public, obviously, in exchange for working on it and doing the data reduction. But you get to know the ins and outs of your data, and you know, great science happens. Our next annual collaboration meeting will be in Chile, and that's because we're all, or one of the reasons that is because we're very excited with our collaboration with our Chilean astronomers, that we're taking a second Apogee spectra to the southern hemisphere. So for the first time, Sloan will be a two-telescope survey. This picture here is our iconic Sloan Foundation telescope, a 2.5-meter telescope in New Mexico. And while the other telescope, the DuPont telescope, looks very different, the dome looks very different, optically the two telescopes are similar. So we're able to take the same design spectroscope onto that telescope and duplicate the survey in the two hemispheres. Now, why would we want to do this, and particularly why for the galaxy survey? Well, of course, that's because in order to see the entire galaxy, we need to be able to view it from both hemispheres. And so here's a visualization of that. You can see here the galaxy, and you see the zoom out here shows the Earth in the right orientation, and our telescope in New Mexico can only see this, outer part of the galaxy. It cannot see the inner part of the galaxy. And in fact, we've been trying really hard to go as far south as possible in observations from New Mexico. We cut down trees even, we point near the horizon, but you can only go so far without actually taking your telescope to the southern hemisphere. And so that's what's happening right now. And I'm not exaggerating when I say right now. The spectroscope is on a ship right now on its way to Chile. It left Long Beach, California a couple of weeks ago, and it's expected in Chile sometime next week or maybe the week after for a first flight in 2017. We are on Twitter, like everyone these days, and we will be tweeting the progress of the installation of this spectroscope. So that's the future, or the immediate future for Sloan. Let's now move to the press items that are happening today. John and Sten will be presenting about elements of life in the Milky Way from the Apogee survey. Johanna will talk about how we use compositions from the Apogee survey to infer something about the planets that might be orbiting them. And Kelly will be talking about our efforts to foster inclusion in astronomy.
Hi, good afternoon. I'm John Holtzman. I'm a professor at New Mexico State University and a survey scientist for the Apogee 2 project. One of the things that I find particularly exciting about astronomy is that it's what I kind of consider a crossroads science. I tell this to my intro astronomy students, that it got elements of physics, elements of chemistry, elements of geology, or maybe planetology is more appropriate, elements of biology, and all kind of wrapped together in this language of math. And I think that's kind of a cool way to think about astronomy. It's really a multidisciplinary science. And today is kind of particularly fun press conference to do because we're going to touch on some aspects of chemistry, some aspects of planetology, and some aspects of biology. And so starting with the chemistry part, you guys probably all recognize the periodic table, which is an inventory of all the different elements as a chemist might see them. Typical astronomers might have a different kind of view of the periodic table, something that looks like this. This periodic table represents the relative abundance of elements in the universe. As you probably know, most of the universe is made up of hydrogen and helium and just little trace bits of all the other elements, which astronomers affectionately and incorrectly call metals, everything else. This periodic table is what I call an astrochemist's periodic table. To someone who's interested in astrochemistry, there's actually a lot of information in the relative abundance of all of those trace elements. And this is because while essentially all of the heavy elements are thought to be synthesized inside of stars, different elements are synthesized inside of different stars and on different timescales. And the color coding in this image tries to convey that idea that the nucleosynthetic source of different elements comes from different types of stars. And from an astrophysics point of view, the main result that Sten's going to talk about here in a minute is to try to use this information to kind of disentangle how a given stellar population came to have the abundances that it did, so to disentangle the chemical evolution history of a given stellar population. Finally, this is the biology part, a periodic table that highlights the 6 elements that, as far as we know on Earth, are found to basically exist in all life forms. These 6 elements are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And I'm told that that is pronounced schnapps. So the biology story of today, which really I do consider kind of a human interest story, is to describe how the abundance of these key elements of life actually is not the same at all locations in the galaxy, but varies from one region to the other. And to tell you how we go about doing that, I'm going to turn this over to Sten, who's my PhD student at New Mexico State.
Hi, my name is Sten Hasselquist. I'm a PhD student at New Mexico State University. And we're able to make maps of the elements of life in our Milky Way galaxy thanks to the APOGEE portion of SDSS. And APOGEE is able to do this because it operates in the near infrared and it can penetrate the dust layer that's in our Milky Way. So as you can see in this image here, you've got the plane of the Milky Way, which has a lot of dust in it, which typically obscures stars when you look in the optical, but the infrared allows you to see much farther, and APOGEE is able to observe stars throughout much of the galaxy. And it can provide detailed chemical abundances for these stars, up to 20 elements. And so here's kind of how we do that. APOGEE records a spectra for the stars it observes. And what a spectra is, it just tells you the brightness of light at different wavelengths of infrared light. Here we have the spectra of 5 different stars, so 5 spectra for 5 stars. Each of the hundreds of dips that you see in the spectra are where an element has absorbed that little bit of light. And the more of an element you have in a star, the deeper the absorption lines are, and the more of them there are. So the top star there you see has a relatively low abundance of elements compared to the bottom star with many, many, many dips. So the chemical abundance of that star is quite high. And if we focus on just certain parts of the spectra that tell us about certain parts of the elements, we can then make maps of the galaxy, since we have these for hundreds of thousands of stars throughout the galaxy. And so here's a little summary slide of that. First off, on the left, we're highlighting the elements of life that we can trace in the galaxy. So here's the human body. Here you've got oxygen in the lungs, blue, for example, phosphorus, red in your bones. The squiggly lines you see on this image, this is one APOGEE spectrum where we've highlighted regions of the spectrum that are sensitive to the different elements of life, for example, green, carbon, nitrogen, and purple, and so on. The center image is an artist's impression of the Milky Way galaxy with actual APOGEE data superposed over top. And what we're showing here, each point you see is a star that APOGEE's observed, and it's color-coded by its oxygen abundance, where the higher the saturation of the color is, the more oxygen that the star has. And so it's a little hard to see this, but what we find is that the inner part of the galaxy actually has more oxygen abundance, higher oxygen abundance than the outer part of the galaxy. And in fact, we can look at this for all the elements of life, carbon, nitrogen, oxygen, phosphorus, sulfur, and we find the same story. So these are similar maps to what we had in the center of the last figure. This time I've color-coded them in such a way where red is high abundance, green to dark green is lower abundance. And you can see in each of these maps that the inner part of the galaxy has a higher abundance of all the elements. And astrophysically, what this means is that star formation in our galaxy proceeded much faster, at a faster rate in the inner part of the galaxy than the outer part of the galaxy. And since we know that, or at least we think that in the beginning of the universe, we didn't have any of these elements, they were synthesized in stars, this implies that the elements for life were available in the inner part of the galaxy for a longer period of time than the outer part of the galaxy. And we don't want to speculate on what that means for the chances of life in other parts of the galaxy. But it is very interesting that we can make these maps, and the data are all public, so not only can we make these maps, but you guys in this room can download the DR13 data release and make the maps yourself. Another interesting part of these measurements is that the chemical abundance of planets typically reflects that of their host star. And so to tell you more about that, I'm going to turn it over to Johanna.
Great, thanks. So my name is Johanna Teske. I'm a postdoctoral fellow at the Carnegie Institution for Science. And today I'm talking about exoplanets and their compositions as inferred from APOGEE abundances. And so I just have pictures of some of my collaborators at the bottom. Wendy, Jennifer, and Scott are all from OSU, Ohio State University, and Cayman Unterborn is at Arizona State University. So as Sten said, host star composition provides a constraint on the compositions of exoplanets. There are a few other ways that we can learn about exoplanet composition, for instance, by studying their masses and radii, or getting atmospheric spectroscopy to determine what's in their atmospheres. But both of those measurements are usually hindered by the amount of time you can get to observe planets. And so it's only possible for a small number of planets. But the host star measurements can be made pretty much on any star that we know has a planet. And these help us, like I said, constrain the initial planet-forming ingredients. So why should you care about exoplanet composition? We know they're there. Why do we care what they're made of? It's related to habitability, although I'm going to refer to it as Earth-likeness in this talk. We were trying to shy away from habitability because that's a pretty complex term, but Earth-likeness is something that we can actually quantitatively determine. And so composition is related to Earth-likeness through all these different processes. The composition of a planet controls what type of atmosphere it has and whether it has a climate, clouds. That is in turn affected by and affects tectonics in a planet. And those two things help recycle material from the outside of the planet to the inside of the planet. And then tectonics at atmosphere and climate are both related to the magnetic fields of planets as well. And so all of these processes are influenced by the composition of the planet. And so in this study, we took host star abundances from the APOGEE spectrograph, that survey, and put them into several different models that started with condensation of different elements from a nebula around a star, and went from there into differentiation of a solid planet core and mantle and crust. And what's particularly interesting about our study is that we're able to start from the solar composition and reproduce what we know is true to be the composition of the Earth to very high precision. And so that gives us confidence that doing this on a different star with a different composition will give us an idea of what that planet might be like and how Earth-like it might be. And so I brought some props. So two of the interesting minerals that we've been studying are olivine, which, as you can see, is this bright green crystalline structure element. It's magnesium rich, and it's a little bit softer than garnet, which is another mineral, more silicon rich. And both of these are different phases of silicon and magnesium minerals that we found in our planet models. This is important because olivine, because it's much softer, and less stiff than garnet, it helps facilitate plate tectonics in planets. And we saw on the last slide or two that that really is important for a planet being Earth-like. And so focusing on a couple of planets that we studied, the two that I'm showing here are a representation of a planet around Kepler 102. And so this star is actually known to have 5 small, probably rocky planets. This is just a general model of a planet around the star. It's not for a particular one of those known planets. but we know that that star has rocky planets. Kepler 407 is another host star, but the magnesium to silicon ratio in this host star's atmosphere is much lower than it is in the Kepler 102 host star. It's actually about 2/3 less than that in the sun. And so as you can see, the different abundance patterns in the star result in different compositions in the planet. Both of the planets have a liquid iron core, and then a layer of bridgemanite, sort of right after the core. But then the upper mantle composition is very different. And you can see in Kepler 407 that there's this red layer of garnet, which we think would prohibit or make less probable plate tectonics in a planet around that star. So we're in the process of extending this study to do more of these types of models for more Kepler planets, stars that host known small planets. And so we have plots like this with the magnesium to silicon ratio from the host star versus the predicted density of the planet, which is actually something we can then check when we have the planet mass measurements. And then you can see we also have a diagram of the predicted core mass percentage for all of these planets, and the sun is there for reference as well. So I think this is really exciting work. We're combining astronomy and geology and geophysics. The takeaways from my presentation are that host star abundances from APOGEE and SDSS really give us an important constraint on the interior compositions of exoplanets and their interior structure in ways that we really can't get from any other observations. Our results point to a wide variety of known rocky planets, but what's particularly important, I think, is we can use this type of information to really hone in on the planets that are most Earth-like and use those as input for target lists for next generation telescopes and JWST. So thanks very much. Introducing. And now Kelly will talk about inclusivity in SDSS.
Hi, folks. I'm Kelly Holley-Bockelmann. I'm a professor of astrophysics at Vanderbilt University, and I wanted to end our press conference today by talking to you about some of our continued efforts to foster a more vibrant and welcoming and productive Sloan Digital Sky Survey. And as soon as it flips to the, oh, there, it was me. I had to flip. Did I mention I'm a nervous speaker? So let me please just set the stage first. In the US, on the left, you will see the US population as gauged in 2007. You can see that roughly 30% of our US population identifies themselves as racial minorities. And in astronomy, this is confined to the top 40 astronomical institutions. Roughly 3% identify themselves as those same minorities. And this mirrors in our SDSS survey. So roughly 10% of our SDSS survey is composed of these same minorities. And this is a long-standing problem in our field. And the Sloan Digital Sky Survey realized that, with such a rich data set and such complex astronomical problems today, we are limiting ourselves if we just confine ourselves to having only one sector of our community look at the data and to do the science. And so we may be limiting ourselves to discovering the next big thing. So we decided that it was time to maybe move beyond talking about the problem and to start instituting programs that may address the issue. And so we developed a committee called COINS, which is the Committee on Inclusivity in SDSS Science. And we were charged with looking at easily identifiable barriers to inclusion and equity in our survey. And we noticed some 3 easily identifiable and addressable things, the first of which Karen mentioned, and that is that it's very expensive to join the survey, to have access to proprietary data, and to a network of world-class scientists. I don't know if I'm supposed to mention how much it costs, so maybe if you are interested, you can ask a question. So not only is it expensive, which means that only the very wealthy and large universities have access and ability to join the survey, but one thing I noticed when I joined is that as a new member, there's kind of an insufficient on-ramping, just in general, to be able to access the data and know how to join a project. So we needed some more mentoring for new members to be able to join the survey and start producing science. And finally, there was a lack of financial support and research opportunities for young students. And so we proposed that we would start a program called FAST, which I'll explain because that's the one that I'm in charge of. But we also started a research experience for undergraduates. Nancy Chanover is in the audience. Raise your hand. Wait. And she will be available to answer questions about that. And also, sorry, there's a ton of FAST and REU students here and mentors. Can y'all raise your hands? So all these people are available to talk to. And some people are afraid to raise their hands. So, let me just explain what the FAST program is. FAST stands for Faculty and Student Teams. And what is designed to do is to target and recruit faculty who have a track record of working and mentoring underrepresented minorities, and to bring them into our survey to form long-term research partnerships within our institution. And the interesting thing about this program is that it's meant to be long-term. So we decided to target faculty because even after this funding would end, we would have enough training and folks who are in the survey to be able to help underrepresented students downstream. So the design is to foster and support folks as they transition into the SDSS collaboration. And I just want to say, it's kind of one of the first questions I get is, what is an eligible FAST team? And it's really hard to describe, and kind of on purpose, because we didn't want to exclude people by having a very rigid definition about what a FAST team is. But broadly, it's a faculty member and some number of students who are some number of minorities, and they may be high schoolers all the way up to PhD students. And typically this team is paired with an SDSS collaborator, one or two, and together they work on a research project. Not only are these, let me just tell you what the FAST teams get. First of all, they get free membership into the collaboration, so the faculty are members of the collaboration in perpetuity. They have access to proprietary data and also to 500 world's experts in SDSS science. So not only do they have access, but they are mentored and trained mostly by their SDSS partner. In case the faculty needs summer support because of high teaching loads, they are given that. They get to come to SDSS meetings and AAS meetings, so they can interact with the broader astronomical network. Students get research stipends, et cetera. In the interest of time, I'm not going to go into a lot of our teams in detail, but I just wanted to show you some pictures. We have 6 teams of 23 students from UCSD, University of California, San Diego, from DePaul University, from City University of New York, and from New Mexico State University, all working on many of the different surveys, from MANGA to TDSS to BOSS. And to end, briefly, I just wanted to give you a snapshot of where we are after 2 years. We have, again, 23 students. Roughly 57% of those are women. Roughly 2/3 are identified as underrepresented minorities, and greater than 25% are first-generation college students. I'm saying greater because I asked over email and not everybody answered the email, so at least that number. We have at this meeting 15 abstracts from our students and faculty, and there are brochures so that y'all can go visit everybody. Oh, Jordan, thank you for handing those out. And I think the most valuable thing for me is that before this program started, there were 4 of our students who hadn't considered a career in astronomy, and now they have decided that they're going to go on to earn a PhD in astrophysics. So I think that's it. Thank you very much.
And thank you all very much. Okay, for the question and answer period, we'll start here in the room. Please raise your hand if you have a question. Larry will bring you the mic, and then tell us your name and affiliation and who your question is for. So, questions. We'll start, Larry, down here with Ethan.
Hi, I'm Ethan Siegel from Starts with a Bang, science writer. I thought I would ask Sten a question. Sten, you said we don't want to speculate about what this means for the possibility of life in the inner parts of the galaxy. I would like you to speculate. Do you have any speculations that you can share?
Well, I don't want you walking out of here writing down that we found life in the inner galaxy, but I mean, me personally, it is very interesting that the elements in the inner galaxy are so enriched, and which means they've had billions of years longer to maybe develop life. But the problem is we still only have one version of life that we know of, so I think that's all I'm going to give you. The longer time scale is tantalizing.
John, would you like to speculate?
As Karen said, there is a reason why they put the Star Wars capital towards the center of the galaxy.
Current there first.
I did say that, yeah. Yes, I did.
Okay, more questions from in the house. Don't be shy. We got one down here. Tell us who you are, who you're with, and who you're asking a question of.
Hi, I'm Corey Johnson. I'm from West Texas A&M University. Is it on?
Yes.
Yeah.
Okay. I'd like to talk to Kelly a moment about your attempts and SDSS attempts to become more diverse. I really liked your brief mention of the programs that you're doing. I'm wondering, you specifically mentioned race and you briefly mentioned women at the end and first-gen college students. How broad are you guys going with the idea of diversity, and are you also doing it not just with programs for like REUs and new students, but are you guys also trying to work on your own staff and add more people to that actually work at SDSS permanently?
This is a really great question. We started with this because it was an easily identifiable charge that was actually given to us by the Sloan Foundation, who, by the way, funded the program very generously, and we really appreciate that. But that's not all that we're doing in COINS. One of the things in COINS that we are doing, which I think other people can speak to as well, is to dissect and analyze our techniques for recruiting leadership. And so we are trying to overhaul the way in which we have a more inclusive and welcoming staff and leadership. And I could talk more if you come up.
Any other questions? Do we have some questions online? All right, Inga, go ahead.
Question from Govert Schilling, freelance from the Netherlands, for Sten. You said a higher CHNOPS abundance in the central regions of the galaxy might be beneficial for the emergence of life. Do you believe this positive effect is stronger than the negative effect of more stellar explosions, lethal radiation, etc.?
Well, I'm not really sure what effect wins out because we don't know of any other life in the center of the galaxy. But yeah, more vigorous star formation would mean much more supernova, which could be bad if you live on a planet and your next door neighbor star blows up.
Well, potential AGN feedback too.
Yeah, or if you're too close to the center of the black hole and the black hole starts accreting things and you get irradiated that way, that's also bad.
That's why you did probably.
That's why I didn't speculate.
Thank you.
Anything else? All right, my turn. All right, I have a question for Karen. I'm assuming, perhaps incorrectly, that the imaging part of the Sloan Digital Sky Survey is where you draw targets from for spectroscopy. And if that's true, how are you picking spectroscopic targets from Chile where you didn't have an imaging survey?
So the imaging that we did in the Sloan Digital Sky Survey was optical imaging, and we avoided imaging the galactic plane because there's a lot of dust. As Sten mentioned, you don't see very far. So the APOGEE survey has been targeted off the 2-mass survey, even in the Northern Hemisphere, and we'll be continuing to do that in the Southern Hemisphere. And of course, the 2-mass survey had 2 telescopes and all sky coverage.
Okay, good. And I had a question for John or Sten. Doesn't have to do with life. To the extent that we can tell, and I'm not sure how much we can tell, but is star formation more intense, or did it peak earlier or something like that in the inner parts of other galaxies that you can see, out in the early universe, or is there something unique about this profile that you discovered in our galaxy?
I think that age gradients, which are actually being probed some by the MANGA survey, generally in massive galaxies have a similar thing, where star formation proceeded earlier in the inner parts of the galaxy. However, in some dwarf galaxies, it's actually the opposite. So it's probably somewhat of a mass or environment-dependent effect.
But do you have the same kind of abundance information, relative abundance information for other galaxies, or is it too hard to get that because they're so much fainter?
So if I jump in, scientifically, I work most with the MANGA part of the survey, and we can get some of these abundance measurements for, eventually we'll have almost 10,000 galaxies. It's not to the level of detail that APOGEE is able to get abundances in stars in our own galaxy, because we don't have the same spectral resolution, so we aren't able to pick out as many. We do the lumping everything into metals kinds of things. To some extent, we do separate it a bit, but we are looking into these abundance gradients and how it changes by type of galaxy, inner structures, where the galaxies live in the universe. But broadly speaking, most galaxies are older in the center and younger in the outer parts.
But a key difference is that in external galaxies, you don't observe the individual stars, you observe the amalgamated light.
Right.
And so really the idea is to use the Milky Way as a kind of Rosetta Stone to say, hey, when you see all the stars lumped together, can we use the Milky Way to help untangle what different components of populations might be making up that integrated light?
So it's like providing a template, basically, that you can compare what you see in other galaxies. Okay. I have a question for Johanna, which may indicate that I've become dyslexic, but I thought I heard you say that that you get garnet in a situation where there's more silicon. But then when you showed the cutaways of the 2 planets, it looked like you were saying that the garnet was in the more magnesium-rich one. So did I just get that mixed up?
Or I said it incorrectly.
Okay.
The star that had the lower magnesium to silicon ratio, so less magnesium, more silicon, is the one that had the planet with the layer of garnet in the
so
upper
it did.
mantle.
Okay, good. So more silicon gives you more garnet.
Exactly.
Okay. I thought, yeah. All right. And then finally for Kelly. To what extent are you, this is the first that I'd heard of these programs within SDSS, and I'm wondering, I know you're giving talks on them here at the meeting. Is this the first that the rest of the community is hearing about them too, or is there some program by which you're hoping to get these kind of programs replicated in other projects?
Thanks. I think this is the first time we've advertised them. I'm the PI, and I'm really horrible at talking to other people and advertising what we're doing, and I'm much more concerned at making sure the students have practiced their posters and are talking to one another. And so I've really been concentrating on trying to make the program work rather than talking about it yet. But we've had 2 years, and so I think it's time where we can start telling people about it. It's not an effort to get it duplicated, but if you want to duplicate it, you can chat with us about things that may be good to try.
And then one other thing, I see there's 4 samples up here, but Johanna, you only showed 2. I'm just curious what the other 2 are.
Sure. So this was the olivine sample. This is also olivine. It's just in a different form. It's not as obviously crystalline. And then these are both different kinds of garnet. So these are all rocks from our planet, Earth, but by volume, Earth is mostly composed of olivine. So garnet is, like what I said, would be a very different type of planet if it had a lot of garnet.
Okay, I've given you all time to think of some other questions. Any other questions? When I was the editor-in-chief of Sky and Telescope, I used to tell my editors, when you go to a press conference, if you don't have a question, you haven't been listening closely. Does that motivate anybody? No, now people are leaving. Okay, I get it. All right, all right. Any more online, Inga? No? All right. We'll wrap it up then. Thanks again to our speakers, and thanks also to Jordan Raddick, PIO for the Sloan Digital Sky Survey for helping put this briefing together.
It's been
Larry, pardon me?
How are you doing? What are you doing?
You want me to talk about the next press conference? That was the next thing I was going to talk about. Yes, our next press conference is tomorrow morning at 10:15 on stars in interstellar space, and then we'll continue again in the afternoon and 2 more on Saturday. So thank you very much. We'll see you tomorrow morning.
Yeah.